This is section 1.1 from Math 1114. In it, you'll get some definitions, some notations. It's a good introductory section to begin. First, we start with the definition of a linear equation. The standard form of a linear equation is a1x1 plus a2x2 plus a3x3 plus however many variables we have up to anxn is equal to b. In this, the a sub i's are constants. They're coefficients, just like we're used to seeing. The x sub i's are variables, and the b is a constant. Perhaps you're used to seeing x, y, and z instead of x1, x2, x3. The subscripts just give us a little more flexibility, so we're not tied to the alphabet so much. The b on the right is the constant. It can be any number. In short, a linear equation contains no products of variables, no functions of variables, and no powers of variables other than the first power. If a variable is present, it must only be to the first power, not to the -1 power, the second power, etc. Let's look at some examples next. Are the following equations linear or nonlinear? Here we have 3 sine x plus 2y minus z is equal to 5. As you see, the 2y and the minus z are fine. The 5 is also okay. But the sine of x presents a problem because that's a function of a variable. It's the function of the sine. So that one was not linear. Let's look at another example. Here we have 2 absolute value of x1 minus 3x2 plus 6 is equal to 0. Here the 3x2 is fine. The 6 is okay. The 0 is fine. But the absolute value of x1, again, that is a function of a variable. If you think about what the absolute value function looks like, it makes a V shape. That's not a line, so that's not linear. The next example, we have 1 over x1 plus 2x2 squared plus sine of pi over 4 minus 3 is equal to 0. Here, the 1 over x1 presents a problem because that's x1 to the -1 power. We also have x sub 2 to the second power. That's not to the first power again, so that also presents a problem. So this is already not linear. For the record, though, the sine of pi over 4, perhaps you remember no trig whatsoever, but that is a number. So the sine of pi over 4 would have been fine by itself. So is the 3, of course. But the x1 to the -1 power, the x2 to the 2 power, that's going to cause it to not be linear. Let's look at some more examples. Here we have x1 times x2 plus 3x2 is equal to 0. x1 times x2 is a product of variables, so this is not a linear equation. The next one, we have cosine of pi over 3 times x1. You notice the cosine of pi over 3 is in parentheses. That is a number. Again, maybe you remember no trig whatsoever, but it is a number. So we have a number times x1. That's fine. We then have minus 1/4 x2 minus 3 is equal to x3. All of that's fine. That is a linear equation. Next, we have the square root of 3 times x plus 4y is equal to 6z minus pi squared. You notice that the square root does not extend over the x. So we have the square root of 3, which is a number, times x plus 4y. Those are all fine. This is a linear equation. The pi squared, pi is about 3.14. If you square that, you do get a number, so this truly is a linear equation. Next, we have a definition. A system of linear equations is just a set of one or more linear equations. A system of equations is square if the number of variables equals the number of equations. So simply count the number of variables, count the number of equations. If they're the same number, then it's a square system. A system that is not square is called rectangular. That's pretty predictable, huh? Let's look at an example. The following system is square because there are two equations and two variables. It's called a 2 by 2 system. As you see, you have x1 and x2. That's two variables. There are also two equations. Therefore, it's a 2 by 2 system. You do count the number of equations first. So if there were more equations, for example, if there were 3 equations and 2 variables, it would be a 3 by 2 system. This system does have a solution. x1 is 1, x2 is 2. You can check to see if it's a solution by plugging in the 1 for the x1 and the 2 for the x2. As you see, 1 plus 2 times 2 is 5. 3 times 1 minus 4 times 2 is negative 5. So this really is the solution. Any system which has at least one solution, such as that one, is called consistent. A system that has no solution is inconsistent. So if I can find just one solution, or maybe a whole lot of solutions, then the system is called consistent. Otherwise, inconsistent. Here are some examples of some inconsistent systems. We have x1 plus 2x2 is equal to 5, and at the same time, x1 plus 2x2 is equal to 3. That's obviously impossible. If x1 plus 2x2 is 5, then it still ought to be 5 in the second equation. So this is an inconsistent system. Let's look at another. This one's not quite as obvious. x1 minus 2x2 is 5. 2x1 minus 4x2 is equal to negative 3. As you see here, the second equation is almost double the first. I multiplied the x1 by 2, I multiplied the negative 2x2 by 2, but I didn't multiply the 5 by 2. If 1 times something is 5, then 2 times something ought to be 10. Otherwise, it's just not going to work. So this is an inconsistent system. Sometimes inconsistent systems are easy to recognize. Other times it requires a little more work. These were pretty easy to recognize. We also need to know how to form an augmented matrix. To make an augmented matrix, put the coefficients on the left and the constants on the right. So as you look at your system, find the coefficients, put those on the left of the matrix. Sometimes you want to draw a line between the coefficients and the constants, and then put the constants on the right. As an example, write the augmented matrix for this system. x1 plus 2x2 is equal to 5. 3x1 minus 4x2 is equal to negative 5. We want to put the coefficients on the left. So the 1, the 2, the 3, and the negative 4 are on the left. Then I put a line, and the 5 and the negative 5 are on the right. The line doesn't have to be there. Sometimes you'll see it there, sometimes you won't. It stands for an equals. So it's sort of an optional thing. If you want to put it there, great. If you don't, that's okay too. Note that when you're looking at this augmented matrix, each column on the left corresponds to a particular variable. So if we're thinking about the system we had before, the 1 and the 3 correspond to the coefficients for the x1. Each row corresponds to an equation. The 1, the 2, and the 5 all came from the first equation. 1x1 plus 2x2 is equal to 5. The ijth entry is the entry in row I and column J. For example, the 1, 1 entry, that would be the entry in the first row and first column. That's denoted A sub 1, 1 is 1. The 2, 1 entry, which would be the entry in the second row and first column, is a 3. So we go to the second row, first column, and you see a 3. That concludes section 1-1. You should be ready after you work a few homework problems to do the quick test, which is the quiz on this section. I wish you the best of luck. Contact me if you have questions.